Okay, so this is the second video in our series covering Chapter 6 for the Math Links textbook. So 6.2 is interpreting graphs. So we're going to be looking at a graph and interpreting data from it, predicting data, estimating values, but essentially you're using data from a graph or a table of values to make predictions and estimates. Before we really get into it, the key terms in this chapter are interpolate and extrapolate. Now, I want to clarify that down the road in grade 10, 11, 12, you don't necessarily use these terms very often. You'll use them when you're talking about very scientific work, but a lot of the time we'll just say estimate between, estimate ahead, predict. Predictions and estimations are essentially extrapolations and interpolations, but in terms of this chapter, when you're asked and it's using the language, interpolate means estimating between two given values. So this would be like if we're driving from Regina to Moose Jaw, and you know the time you arrived in Moose Jaw and the time you left Regina. If I asked you what time did you pass Belle Plaine or what time did you pass Pence, estimate that time. That's interpolation because you're interpolating between two values we already know. Extrapolate is predicting the future. It's going beyond what you know. So this would be like if we left Regina and we have a measurement for what time you arrived in Lumsden, what time you arrived in Chamberlain, what time you arrived in Davidson. What time do you think, or can you estimate the time you're going to arrive in Saskatoon? So that's interpolation and extrapolation. It's just two forms of estimation that we'll be using. Now, the first example here, solve a problem using interpolation. We're going to see a graph of this on the next slide, but I want to look at the table of values first here. So we're talking about a weather balloon that's recording air temperature at different altitudes or heights in the sky. The data is approximately linear, which means that it's mostly consistent, or it is consistent, but because it's real data, there's other margins of error that might make it not a perfect linear relationship or not a perfect line. And we talked about linear last section, where linear means the data is consistent and it mostly lines up. If you plot it on a graph, you should be able to connect the dots and it'll make a solid line that you can connect with the ruler. So because it's real data, that's why they say approximately represents a linear relationship. So in this case, interpolate the approximate value for the air temperature when the balloon was the height at 600. So they're just giving us a height or giving us altitude and asking us to approximate the temperature. So if we look at this data, we can see we're given altitude in meters, so 350, 750, 1,000, 1,500. And we're given temperature in Celsius. So you have 11.4 Celsius, 5.7, 2.1, -5, and -10. A couple things that are important to recognize. Just by looking at this, you should be able to tell that altitude is increasing and temperature is decreasing. On a graph, you'll be able to physically see this because as the altitude increases, the temperature lines actually go down. But on a table of values, you should be able to see that, and that's part of what's going to tell you the relationship. So we know this is true because as you go higher and higher, the temperature gets lower. That's why there's snow on top of mountains. So when we're given 600, the reason it's interpolation is because it's between these 2 points we already know, so 750 and 350. Now, you could just pick an estimate based on the distance, but one way to really get a bit more of an accurate estimation is to approximately or quickly find what halfway is. So to find halfway, you're just going to subtract the larger value by the smaller value. So in this case, 750 minus 350 gives you 400. That means there's a difference of 400 between them, or if you divide it by 2, 200 would be halfway. So 350 plus 200 is 550. So that's halfway between, and you can confirm that by adding 200 again, which gets you 750. Now, between 11.4 and 7.5, you can type this into your calculator, but that's going to give you 5.7 again. So the difference between them is 5.7. So you can find the halfway of that, but you are just approximated again. So if you know the full distance is 5.7 or about 6, then you can just add half of 6. So 3 in this case. If I just added 3 to 5.7, that gives me 8.7. So this isn't exact, that's a quick estimation, but 8.7 is the approximate halfway point. Okay, so now that you know the approximate halfway point, you know 600 is going to be after that. You can make any estimate on this. You know that you have almost another 3 to go here, and 600 isn't quite a third. 600 is technically 25% of the way to 750 from 550, but I know that means it's going to be near a third. So if you went down by a full 1, that's 7.7. So I would guess 7.9, 7.8, even 8. Any of those are good answers. You're just estimating in this case. You're approximating when you have this. When you have a graph, you can get a bit more precise potentially, and when you have the equation, you can get even more precise. But when you're just estimating, use halfway and then find an approximate value that makes sense. For B, we have 7.5 Celsius. So if I go here, we can actually see 7.5 is already halfway because we have -5, -10, and halfway is 7.5. So at -7.5 Celsius, what's the altitude? In this case, you're just going to find halfway because 7.5 is already halfway. So when we go up top, 1800 and 1500, there's a difference of 300 there. So if I go up by 150, that's going to give me the halfway. So 150 plus 1500 is 1650. And so because this is halfway, 1650 is actually the answer there. So at -7.5 Celsius, you're going to be at approximately 1650 or 1650 meters. And lastly here, it's asking, is it possible to interpolate precise values for the air temperature when they're giving you 1050.92? The answer is no. And the reason is you can't be precise because you're dealing with huge numbers. These are going up by hundreds. So when your numbers are going up by such large amounts, you can't really look at the decimals unless you have more measurements or more data points given to you. So if your data points were going up by 5 or 10, you could possibly be precise with this, but because they're going up by hundreds, really you can't be too much more precise than 50s and stuff. So this is interpolating using a table of values. Now if I go next here, this is actually a graph giving us our altitude and our temperature. And we can see they've plotted the points on here, and the 2 questions we were given are actually kind of marked. So in the first one, we were given 600 and asked what the approximate temperature would be for it. Now on here, you can see you just go to 600 meters on altitude and draw a line up or down so it intersects with the line or the data points. And then once you get that point, you're going to look to the left and try to figure out what the approximate value to the left is. So in this case, they went up to 600 and it was a bit above the halfway point between these two, so they guessed 8. If you can remember, we guessed 7.9, so we were pretty spot on to 8. So that's how you figure it out with a graph, is you go up from the one value and then left to the other value. So in the case of altitude, we were given, in the case of the second question, we were given -7.5 as our temperature. So you go to -7.5 on the temperature axis or the vertical axis. Then you draw a line with a ruler all the way so it intersects with the data and the line here. And go up and you can see the approximate point here. Now in this case, they guessed 1700. I wouldn't personally guess 1700 only because of the fact that you can see where this lines up. It wouldn't be 1700. You know that 1700 is halfway between 16 and 1800. So in this case, it would be more accurate to say 1650 or 1640 or 1630. But what they're doing is they're just saying, okay, this is between 1600 and 1800. So they said 17. So this is how our data on the first slide lines up with the data on the graph. So just before we go into the second question here, I just want to discuss the way the graphs are set up. The horizontal axis is always going to be the more independent of the two variables. So in this case, because we have time versus distance, well, distance can change, but time stays independent and consistent. So that's why time is on the bottom. In this case, we're working with a plane as it lands, the altitude as it lands. So we can see here we have time and altitude. So when it was 20 kilometers, 0 time had passed, but as it was landing, you can see the altitude drops as time moves on. And near the end here, it's getting near 0. So they're asking us, what's the plane's approximate altitude at 50 seconds? The way to do this is you actually need to go on here and you need to approximate, okay, where's about halfway? I'm going to say halfway is there. So once you figure out what your halfway point is, you have to take a ruler and you have to make one of those boxes that goes up to the graph. So I'm going to turn on the PowerPoint ruler here. And we're going to switch it to 90 degrees because that's up and down. But for you, you're just taking your ruler and you're lining it up with the point. And I'm just going to line it up with my point here and draw a line. So once you have your line drawn, you're going to look and you're going to see where it intersects with the graph. And then you have to take your ruler again, and you have to figure out where that lines up with the side or the other axis. And it came out right on 10 almost. So we're going to say that at 50 seconds, the altitude is 10. Now I want you to quickly pause the video and try this on your own. So find 11 kilometers on the altitude and figure out what the time would be for 11 kilometers. And I'll give you a second to do that. Okay, so for 11 kilometers, what we have to do is we have to take the ruler and we have to approximate where 11 is going to be. Now you can do this by drawing lines on the graph. So I'm going to take a red pen here and I'm going to go 14, 13, 12, 11. So that's my approximation for 11. That's not perfect, but that's okay. So then we're going to line up the ruler with 11 and draw a line. Now, once you have 11, you're going to take your ruler and you're going to find out vertically where does this line up with the bottom axis. So I'm going to say it's approximately there. And you're going to draw that line. So now that you have this here, you can see that you have your two lines and you just have to estimate where the value is here. So I'm just looking at this and I can see that it's about halfway between these. So between 40 and 50, it's about 45. 43, 44 would be good too, but I'm going to say 45 for mine. So at 45 seconds, it was at 11 kilometers. At 50 seconds, it was down to 10 kilometers altitude. Lastly, is it appropriate to join the points with a straight line? The reason they're asking this is you have to say, is there subunits here? So we have time, and we have these points between time. Is it appropriate to have smaller points in between those? Because when you draw a line, you're saying that every single point on that line is an accurate point. So in this case, when you're dealing with time, you can go down to seconds, milliseconds. So yes, it's appropriate to have a line there because this is a continuum. If you're dealing with something where you have computers or if you have persons or units, and you can't have a half a unit or a half a person, that's when it's not appropriate and you don't want to draw a line because the line would then tell you that you can have half a person and a quarter of a person. So that's how you figure out if it's appropriate to join with a line. Now, for the next one, we're going to talk about extrapolation. So, extrapolation is just predicting ahead of time. So in this one, we can see Anna's kayaking east near Queen Charlotte Islands. They're also called Haida Gwaii now, towards Graham Island. And you can see her course is drawn by the map here. There's a little arrow here. You're trying to approximate or extrapolate the coordinates for the latitude and longitude where she's going to land. So you can see going up here, they've already actually predicted what point she's going to hit the island. They've done the ruler work, but you would find that with a ruler. But now that they've found that, we're just going to try to guess what the latitude and longitude is. Or in other words, what's the x and the y. So I'm going to start with the horizontal, or in other words, the measurements on the top here, because that's going to be your first value. So we're going from 132 to negative 131. And this would be about halfway. So you could say it'd be negative 131.75, 0.8. You're just kind of guessing where it's going to be. So you can see this is just after negative 132, or just before it. So that's why you might say the first value would be negative, I'm going to say negative 131.8 degrees. For this one, you can see the scales went up a bit. So halfway is going to be about there. This is almost exactly halfway up. So I'm going to say it's 53.75. So this would be your latitude and longitude. This is just the estimation part. This is just guessing based on the numbers here in the graph. So all of it is going to be guesswork. Now, the second part is they're asking, could you use extrapolation to estimate where she sailed from? In the context of the graph we have here, you can't, because we don't see the other island. But if you had a bigger map, you can definitely go like this and line up with her line and estimate where she started on mainland or maybe on another island. So you can extrapolate both ahead of time and into the past. It just requires a ruler and lining it up. But in the case of this graph, because we can't see the other island, the answer is no, you can't predict where she came from. So that's kind of using extrapolation on a map, or estimating and predicting on a map. Lastly, your turn once again. The value of a computer decreases over time. The graph shows the value of the computer after it was bought. So we're being asked, after what time does the computer have no value? What time is it going to be approximately 200? And is it appropriate to join the points with a line? So you can see here we have a graph with the years and the value. I'm going to give you a chance to figure out A. So we can see 1,000, 800, 600, 400. Where do you think this is going to end up at 0? Pause the video and just take a guess right now. Okay, so I'm going to use a ruler again. You can kind of guess with your eyes, but you're best off to use a ruler whenever you have one available. So with a ruler, you can go and you can draw here and just extend the line. And I'm going to use green just so we can see where I extended it. So you just go dashes. And we can see here, you can approximate, it's going to hit 0 at about 5 years. Because that's where the line hits here. So at about 5 years is when it hits 0. So the answer for A would then be 5 years. So for B, when would it be worth approximately 200? I actually almost drew a line over this already, so you can pause and guess. You can see here that at $200, it lines up with this blue line. that means it's going to be 4 years. So B says at 4 years, it's going to equal $200. And lastly, is it appropriate to join the points with a line? What you got to ask is, for both of these values, are there subunits? Can you go between these points? If it had something at the bottom where you couldn't have half of that item, that's when it's not appropriate to connect the dots. But in this case, because it's time, you can have smaller units of time, so it is appropriate. So C would be yes. And that is chapter 6.2. So here's an assignment from the MathLink textbook that you can work on to practice these. It's related to the 6.2 content. And in the next video, I'll go over 6.3 for you.